Howdy, everybody. Today we're going to be talking about smart card hacking. And one of the problems with talking about smart card hacking is that people get really mad when you steal their money. The advantage of this particular smart card hack is that this smart card has not mattered since I was a student, which means that we can freely talk about it and we can freely look at all of the details for hacking this card, so that when you look at a new card with different vulnerabilities, you'll sort of already know how to begin. Is anyone here from the Niagara Kudelski group? All right, cool. Thanks for being good sports. The chip that I'm going to be talking about today is a Niagara chip, their ROM3 generation. It was used in this Dish Network card in North America. This was also used in Canal Plus cards over here in Europe. Internally, the chip is a 6805 microcontroller. It has RAM, ROM, and EEPROM. And it has the very nice feature, the 6805 architecture does, that it is a von Neumann architecture and the RAM is executable. The bug we're going to be talking about today allows for remote code execution inside of the chip of this card, at which point you are able to extract the EEPROM that contains the card's identity. If you have the EEPROM and you have a dump of the ROM as well, you can emulate the card, and you can also clone the card into different cards. You can change the number of television channels available, and you can raise the pay-per-view credit balance. The source of the bug, the way that I found out about it, was from plaintiff's exhibit number 98 in a lawsuit between EchoStar and the NDS Group. NDS Group, it used to be a competitor to Niagara, and the allegation in the lawsuit, and at some point in telling these stories, I'm going to screw it up. So to be clear, everything I'm saying is an allegation, even if they did it. The allegation is that NDS hacked the Niagara chip, weaponized the hack. That much they definitely did. The unproven or semi-proven allegation is that they then leaked that hack to the pirate community in order to allow the Niagara cards to be hacked more than the NDS cards were hacked. That's the part that I have no opinion on. If you'd like to hear more about the drama behind that, there's a book called Murdoch's Pirates that describes all of these adventures. It's probably the best general audience book on hacking that I've ever read. The author is more interested in News Corp conspiracies and that sort of stuff, but the technical details and the people involved in them are accurately represented, and it's at a pace that makes it a gripping read, almost like a thriller novel. The threat model of these smart cards was constrained by the technology at the time. Today, if I have code in a card, I can make that card periodically talk back to my central authority. I can not only give the card updates, but I can also request things from the card. In the 1990s, it didn't work that way. The big selling point of satellite TV was that you could have lots of television channels while living in the middle of nowhere. So if you're stuck in the middle of a desert, if you're in a small town far from roads, I know that this is hard to imagine from Switzerland, but there are many countries in the world with empty spots in them. If you're in one of those locations, you could have one of these cards and you have a very fast downlink from the satellite in terms of MPEG video with digital packets attached, but you don't have any uplink at all. So the card would remember which television channels you had, and maybe you also had a telephone line, and you could call home in order to update your pay-per-view balance. When attacking this card, the card itself is very small, you have very few commands to communicate with it, and you have very little visibility. You have no debugger at all. So you really want two different vulnerabilities in the card. The first thing that you want is a hardware foothold, however expensive that might be, to get a dump of the read-only memory. And once you have a dump of the read-only memory, you can start looking for software bugs in its implementation of the protocol. The other thing that you want is, because that hardware attack that gets you the read-only memory is so hideously labor-intensive, you want a software vulnerability that you can very easily reproduce. You want one packet that you send to the card to get code execution and give you all the television channels. But you need both, because you need the expensive hardware attack in order to get the inexpensive software attack. If you try to write the memory corruption exploit without even knowing the instruction set of the card, you're never going to finish. The card itself is from STS-Thompson, now known as ST Microelectronics. It's a 68HC05. So if any of you did 8-bit programming back in the 80s with the 6805 chip, this is the same chip. It has a 16-bit program counter. It has 8-bit accumulators and index registers, one of each. An 8-bit index register means that there is no way to dereference a 16-bit pointer. That becomes important later on. You have a 16 kilobyte user ROM and an 8 kilobyte system ROM. You have 512 bytes of RAM, but I'm only able to find 224, and in the same way, not all of the ROM is exposed to the user at any one time. The user ROM is what contains the television code. This is what Niagara wrote. The system ROM was written by STS-Thompson, and that contains cryptography routines that you can call, but you cannot read as data. This means that if I get code execution in RAM, I can dump the user ROM, but I cannot dump the system ROM. And there's also 4 kilobytes of EEPROM that is itself executable. The EEPROM was used for software updates in the field, and these software updates would be sent down from the satellite to the card. In order to understand the card better, I boiled it in acid and I decapsulated it. You notice that there's like this brown sheen over the card. It's kind of hard to see the details in the regions. That's a protective mesh. This is to prevent you from sticking needles into the card. And as we'll see a little later, it didn't quite work. You also have a logo area. Back then, people liked to put art on their chips because they weren't as boring as they are in the modern world. You can see that the chip itself was designed in 1994. The exploit was in 1998, and the lawsuit was in 2001. So we had quite a lifetime on this architecture, with 8 years from the design of the chip until the retirement of the cards. We have a cool little frog here. This is called the ST Micro Frog. You'll see this on all of the STS-Thompson microcontrollers. So if you take the Navigo card from Paris and you boil that in acid, you also find the same frog. You have the initials of the designers. Is anyone here with their initials on the screen? It's a shame, because that'd be pretty cool. There is a public data sheet that contains very little information. There is also a private data sheet that thankfully was also entered into evidence as a plaintiff's exhibit in the lawsuit. So the only surviving documentation that we have for this chip came from the evidence in that lawsuit. The confidential data sheets back then were a lot harder to find than they are now, when they're data sheet sharing websites and things like that. The data sheet also has a memory map. And the details here don't matter so much as that at the very beginning of memory, you have registers. These are special function registers. They're done for things like I/O. These are not general purpose registers like you would have in a modern chip. You then have RAM, and you have a call stack within RAM. And the call stack works just like it would on a PC. The stack goes down. Every time you make a function call, you push a return pointer. When you return from the function, you pop that return pointer back into your program counter. You also have ROM regions, and you have EEPROM regions, and you have gaps between them. And we'll get to why in a minute, but this layout is a lie in that a lot of the unused regions are actually filled with stuff. Your EEPROM is 4 kilobytes at address E000. Because this is a 16-bit chip, and because there's nothing like ASLR to move our pointers around, it becomes handy to start thinking of things as physical locations. So when I'm working on these chips, I always take care to learn the base addresses of the different memory regions and a couple of important pointers. Inside of EEPROM, they had this string, Nipper is a butt licker. Nipper is the dog in the RCA Victor, his master's voice logo that you would find on phonographs in the 1930s. And the purpose of this in EEPROM is twofold. First, if I'm beginning to reverse engineer the chip and I photograph the read-only memory and I decode it, I don't get a copy of the EEPROM. So I only get a copy of this once I'm able to read out the identity of the card with enough detail to copy that card. Second, the string has awkward capitalization, and it's funny. So if I'm reverse engineering this card and I find a string like that, what I'm going to do is I'm going to tell my friends about it. And they're going to tell their friends about it, and some idiot is going to post it on an internet forum, and Niagara Kudelski happened to have an informant that ran the biggest satellite TV piracy forum at the time. So if you could just write in a SQL query that once an hour checks the database of all of the forum messages to see if anybody has ever mentioned Nipper with a capital N and a capital P, and if so, you know that your card has been hacked. There is a British comedy sketch called The Funniest Joke in the World, where in World War II, the British tried to do the same thing to figure out if the Germans had copied their codes. They hired a comedian to write the funniest joke in the world, sent it in their code, never decrypted it, and murdered the comedian, so that if a month later they heard the joke, they knew that the Germans had cracked their codes. You have SRAM. There's very little SRAM in this thing. Allegedly, there are 512 bytes. I've only found 224 of them. They begin at 20 hex. They end at 1FF. These bytes have to contain every global variable, the call stack, and the receive and transmit packet buffer. For efficiency reasons, they use the same buffer for the incoming packet as they use for the outgoing packet. But it is executable. And if you're able to trick the program counter into pointing to this region, you're able to run code there. And architecturally, it's very hard to turn off because the index register on this chip is only 8 bits wide. The only way that you can fetch an arbitrary 16-bit addresses value, the only way you can dereference an arbitrary pointer is to put code in RAM and execute that from RAM, changing the address in the instruction. You have a system ROM. Again, this is written by STS Thompson or ST. You're not allowed to read this from RAM. There is a memory firewall that prevents you from reading this code. The memory firewall also could have prevented RAM from doing things like reading the EEPROM, but the designers didn't use that feature. STS Thompson advertised the feature. Niagara decided not to use it and chose a more permissive layout. You have a user ROM. This is 8 kilobytes at 4,000 hex. This has your satellite TV functions. This is where your UART command handler is. This is the code that Niagara wrote to make this a TV card. You can also photograph the ROMs. Here's a photograph of it. Physically, it's 21 kilobytes in size. Here's a zoomed-in version in MaskROM tool, which is a CAD program that I wrote for reverse engineering photographs of ROMs into their data. And if you look very closely, there are dots and there are lines. Wherever you see a dot, that is a 1. Wherever you see a line, that's a 0. And I can kind of like jump back and forth between the two values of it to show you the bits. The first public exploit for this was released December of 2000. The author copied the Nipper capitalization trick, right? Just like that joke string that was an EEPROM, and did the entire publication in it. It says, there will be no boxes anymore. There will be no more fighting amongst us. Learn from this and prosper. Works across the world. Do the following. Get ATR. ATR is the at reset string. When you first power on a smart card, the smart card sends that string to you to tell you what the card is, what voltages to speak to it, what clock rate it expects, things like that. After that, you wait 500 milliseconds to ensure that the card is idle. You can't immediately transmit to it because it might be doing housekeeping. Then it says to send this packet. 28802 is the ROM revision that is vulnerable to this and to anything earlier. And then you receive 4 bytes plus 4 kilobytes, and you have the entire EEPROM. And it just provides the exploit string and nothing else. This was the first publication that allowed you to hack this card. If you send that string to the vulnerable card, it will vomit back a copy of the EEPROM. The way that this works is by putting 196 bytes into a 100-byte buffer, which would be a classic stack buffer overflow, except that this is not a stack buffer. This is a global buffer, and it's at the very end of RAM. So if you believe the layout from earlier, you should be overwriting unused memory. And the shellcode actually executes from address 0060, which is before the buffer that we're writing to. This is the layout as it's in the datasheet, and this layout is a lie. Specifically at the very top where it says that unused memory comes just after RAM. That's not true. What actually is after RAM are ghosts. Not like ghosts and goblins, but ghosts as in mirror copies of RAM. When you're wiring a parallel bus, the address lines control which memory is activated, and then within the memory, they choose which address is activated. When this chip was designed, SGS Thompson wired general regions to their different memories. And then they wired the specifics to those memories. And when you're wiring the specifics for a small region, you have unused address bits in the middle. Kind of like how on a 64-bit machine, some of the bits in the middle of the 64-bit address are unused because our memory management units only support 48 bits out of the 64-bit pointer. Well, they used the same thing back in the 16-bit era. And that means that after SRAM, I get another copy of SRAM. So the way that it works is it throws 196 bytes into a 100-byte buffer, and the buffer is at the end of RAM. Ghosting causes this to overwrite the beginning of RAM. And it starts, it actually overwrites the index that in memory that the buffer is being copied to. That jumps it ahead a little bit, and then it overwrites the stack pointer. This then gets us remote code execution, and the shell code is simply grabs the byte from EEPROM and calls the ROM subroutine to transmit that byte. That was published in 2000, but secretly there was already an exploit that was written in the middle of 1998. This version of the Headend report is from November. There's also an October version that is almost as good, but you want the November one if you'll be reading this. And this is Plaintiff's Exhibit 98 in the lawsuit. This document is about 40 pages total, and it is some of the best literature I've ever read on how to write an embedded systems exploit. The source code is included. It is commented. You're given the loading address as well as the bytes of machine code. the assembly code mnemonics, and finally a full comment of almost every line. David Mortensen wrote this in Jerusalem in 1998. It also explains the initial dump. Because again, in order to write this, we need to first have a copy of the ROM. The way that he got the ROM, and again, this is from court records, so the photograph isn't that great. This piece here is the instruction fetch decode latch of the 6805. The purpose of the instruction fetch decode latch is to hold the opcode of the incoming instruction and to keep it there while the rest of the instruction is being fetched. If you force this to not accept a new value by putting a probe needle on the die of the chip and grounding it, then the program counter becomes a linear counter and it spins through all of memory, fetching every byte in order. And a second probe needle can watch one data bit at a time. And by watching those data bits, it can get a dump of that one bit of significance throughout all of memory. If you do this for all 8 bits and you line them up, you get a full memory dump, including RAM, ROM, and EEPROM of the entire chip. The Headend exploit is 100 bytes of shell code. The string itself is a bit longer. It executes from 19C, so it's executing at a different place in memory than the Nipper exploit. You have 32 lost bytes, which are written to a piece in the ghosting region that is unusable. You have a lot of global variables that are overwritten, and it takes care to overwrite those global variables with correct values so that the chip doesn't crash and it doesn't jump to the wrong clock rate. Some of these I don't think they had the right values for. So the Headend exploit includes its own UART driver in order to make its own serial port transmissions rather than reusing the one that is already in ROM. This is documented with a column for the code, column for the loading address, which is very handy when you're trying to debug this, especially as you don't have a debugger. The full mnemonic, and then comments that explain what everything inside of that instruction is there for. Appendix F dumps out the EEPROM just like the Nipper exploit did. Appendix H gives you every TV channel and maximum pay-per-view credit. You transmit this one packet, it transmits it okay, and you're good to go with all the TV channels. So I wanted to run this myself. I bought a bunch of antique TV receivers on eBay. My front porch was covered with these and VCRs and other dumb shit that they came with. You sometimes get cool silkscreen art, like this is a privateer with the FCC flag. This got me cards. And I had to get the cards from the TV receivers rather than from card collections because of the updates. The in-box TV receiver was manufactured with the card that had never received an update because it had never been taken out of the box. So if I bought the right receiver, new in the box, and it had never been taken out and commissioned, and most importantly, never connected to the right satellite dish, then I could get it without the software update that would remove this vulnerability. I needed a USB smart card reader. These are a little different because the serial port readers will give you a raw communication of the card. The USB ones abstract it away. In the USB reader, the card needs to speak back to you with valid framing and valid checksums. And it has a length restriction according to the protocol. There's no option to just send 4 kilobytes back. I used the Go card library so that I could write the framing for my exploit in Golang. And then I began by just implementing the simplest commands of it. You read the serial number. I then brought in a patched version of the Nipper exploit. I first wrote this by hand by making changes to the bytecodes of the original exploit. That became a hassle. So these days, I have my own 6805 assembler. My assembler takes the .asm file, assembles it into a .go file, including all of the symbols and the bytes. And in honor of David Mortensen's exploit write-up, I also include full comments of what those bytes mean so that if you want to play around with it, you can do it from the Go code without having to have a copy of my assembler. For continuation, I transmit very small portions of the EEPROM. I allow the card to crash, and then I use USB to restart the card in order to try again. And by repeating this many times, I can then dump out the EEPROM, the RAM, and the user ROM. Remember that there is no software currently known that can dump the system ROM. And while I can call functions in the system ROM, there is no possibility of a ROP gadget that would allow me to use the ROM to dump itself, because there are no 16-bit data pointers on this architecture. After I get the dump out, I can run strings on the EEPROM, and that tells me that Nipper is a butt licker. We've hacked the card. This is your cue to applause. There's some other features in this card. SGS Thompson was trying to use this for general cryptography as well as for TVs. So for general cryptography, you need a random number generator. So I wrote shellcode that would do the random number generator. How random does this look to everybody? I think what they're doing here is that they're sampling some like transistor bias or something into an LFSR. And you basically get exactly the same string, except that occasionally it will jump ahead or behind by a bit. Maybe there's a background timer, but never ever build a random number generator this way. It is good enough for a random backoff, though. If I have like a whole fleet of cards and I don't want them to install an update on the same day, this random number generator is perfectly good enough to make sure that they'll have a 3% chance of updating on any given run of the update function, so that I don't destroy my whole fleet with a bad update. There's also this memory access control matrix. This is the memory firewall I was talking about. This is what prevents RAM from reading, this is what prevents code executing from RAM from reading the code in the system ROM. It could have been a very effective defense. And if you read in the datasheet how it was supposed to be configured, the user ROMs were supposed to be completely protected from access to this thing, and they were not. If they had been, then the shellcode that dumped the EEPROM would not have been able to dump a copy of the programming. And the Nipper clause leak would have been enough to allow code execution, but it would not have been enough to allow further reverse engineering of the user ROM by TV pirates. If you'd like to play with this code, it's up on GitHub. You'll need a vulnerable card, so you can buy up all of the old Canal Plus receivers and write your shellcode and then begin exploring from the inside of a smart card. Thank you kindly for your time and attention.
Awesome. Thank you very much, Travis.
Yep.
Do you have any questions?
How did the lawsuit end?
The lawsuit ended with NDS collecting a whole bunch of cash, because if they lost the lawsuit, they would have to pay the cash. They lost the lawsuit, and they appealed. Because they had already lost, they needed to really have all of the money, which they did. They then won the appeal. The judge in the appeal said that it was clearly proven that NDS had hacked the card. It was clearly proven that they had received the television signal without paying for it. But it was only proven that they had done that on one receiver, which had cost the satellite TV company a $23 monthly subscription fee. So the damages were reduced from millions of dollars to $23. This then became a problem because NDS had a whole bunch of money. So they got bought by private equity, which sold the smart card part of the company, which is worth a lot less than the money they had for the lawsuit, to another firm, and then bought it back at a discount a few years later, and this cycle repeated itself until eventually everybody smart left the company, all of the equipment disappeared, and somewhere there's a file cabinet with all of the paper copies of reports like the one that David Mortensen wrote here. And I would love to rifle through that filing cabinet, but so far it's not been found. Any other questions?
No? So thanks again.
Thank you.